Welcome to the Explainer. We usually talk about quantum computing in terms of making faster machines, right? But what if it's actually about something way bigger? What if it's about learning to construct entirely new realities, literally from scratch?
Now I know, that question sounds like something straight out of science fiction. But believe it or not, it's the real question pushing a whole new way of thinking about quantum computing. The goal here isn't just about running programs anymore. It's about literally architecting the universe that those programs exist in.
Okay, but before we get to that amazing future, we gotta get our hands dirty. We have to start right here on the ground floor with a super real and frankly, super frustrating problem that researchers are dealing with, like right now. So what's this big roadblock? Well, it's what people in the field call the hardware gap. And it's this huge bottleneck. Seriously, it's what's holding everything back. Right now, we're in what's known as the NISQ era. That's NISQ for Noisy Intermediate Scale Quantum. And you really got to focus on that first word, noisy. It means that the quantum computers we have today, yeah, they're powerful, but they're also unbelievably fragile. They're limited, and they're so sensitive that even the tiniest little thing from the outside world can throw them off completely.
The public enemy number one for any quantum computer is this process called decoherence. Basically, it's when all that cool quantum magic, superposition, entanglement, all the stuff that makes these machines so powerful, it just evaporates. It just fades away because of interference from the environment. Seriously, it's like trying to build a super intricate sandcastle while the tide is rolling in. It's a constant battle.
And this image, it really drives that fragility home. You can picture a qubit's perfect, pure state as a single point on this sphere. It's this delicate, perfect balance. But decoherence? That's like a constant tremor shaking the whole thing, always trying to knock that qubit off its spot and completely scramble the information it's holding.
So, okay, if the physical hardware is that fragile, how in the world does anybody get anything done? Well, here's the clever part. You don't build in the real world. At least, not at first.
And there's this fantastic analogy for how they do it. Think of these powerful simulators as the sophisticated drafting tables and workshops for quantum architects. Right? You can't build a real skyscraper on a drafting table, but you can absolutely perfect every single blueprint, every little detail, long before you even think about pouring concrete.
And that's exactly why the whole industry has pretty much adopted this simulation-first approach. Instead of fighting with that shaky, unreliable physical hardware from day one, teams are designing, testing, and debugging everything inside powerful classical computer simulations first. They're essentially building a complete digital twin of the quantum system in a virtual world.
And we're not just talking about one kind of simulation here. It's more like a whole toolbox with all these different methods. Now, you don't have to get bogged down in the names, but the big idea is that each one is a specialized tool for a specific job. For example, some are great for systems with lots of entanglement, others for different kinds of circuits. The point is, this virtual design process has gotten incredibly sophisticated.
And these virtual tools, they're getting so fast. I mean, check this out. One new simulator recently clocked in at 137 times speed up compared to NVIDIA's own super optimized library. That's not just a little bit better. That is a game-changing leap in how quickly we can design and test things in this virtual space.
Okay, so designing in a virtual world is a brilliant workaround. But at the end of the day, you still have to run this thing on actual hardware, which brings us right back to the original problem, doesn't it? How do you take that perfect virtual blueprint and make it work on those noisy, unreliable physical qubits? Well, the answer is just genius, really. It's abstraction. Instead of trying to fix every single noisy physical qubit, which is almost impossible, you build something new on top of them, a logical qubit. The core idea is to take a bunch of those flawed physical qubits, entangle them together in a really clever way, and create one single, stable, and reliable quantum bit from the group.
Here's a great way to think about it. Imagine those noisy physical qubits are like shaky, unstable ground. You wouldn't want to build a house on that, right? But by creating a logical qubit, you're essentially building a reinforced, stable platform on top of all that shaky ground. All of a sudden, you've got a solid foundation to work with, built from the very noise that was causing the problem.
And hey, this isn't just some abstract theory. This is happening now. There was a massive breakthrough recently from Quantinuum and Microsoft,
where they actually did this. They created logical qubits that had an error rate 800 times lower than the physical parts they were made from. Just wow. And get this, they did it way more efficiently than anyone thought was possible, using only 30 physical qubits to make 4 logical ones. That is a huge milestone. It proves this whole approach works.
So this power to build stable, reliable systems, this ability to just abstract away all that physical noise, it's not just a clever engineering trick. It's way more than that. It cracks open the door to a really, really mind-bending new possibility.
Because once you can reliably build these virtual systems, you're not just writing a program anymore. It's a completely different game. You're doing something way more fundamental. You are literally designing the very structure of computation itself.
And the tool they use to do this is called a Virtual Quantic Blueprint, or a VQB for short. The best way to picture it is as a complete, living, dynamic digital map of an entire quantum system. It's not just a static set of instructions. No, it's an interactive model of a little quantum universe that you can actually change and play with.
So with this blueprint, you, the designer, have total control over the whole process. You define the starting state of all your virtual qubits. You lay out the sequence of quantum gates that create all the cool stuff like superposition and entanglement. You even decide when and how to look at the system to get your answer. You can even build advanced logic, like error correction, right into the DNA of this virtual reality.
And this whole blueprint idea, it's really just the first step toward an even bigger, grander vision. We're talking about a whole new kind of operating system, but not for a computer, for reality itself. It's called a Quantum Linguistic Operating System, or QLOS.
Now, this QLOS is organized in these degrees of design, almost like a ladder you can climb. Down at the bottom, at degree 0, you have the raw physical hardware, but as you go up, you get more and more abstract. First, you create a virtual lattice, then you get to this amazing glyphic layer, where you define algorithms using symbolic glyphs, and some of these are even inspired by old mystical traditions, which is pretty wild. Go up another level, and you have an AI that actually helps you design and evolve the blueprint. It learns. It's this whole stack, all the way from raw physics up to a 3D space where you and an AI can design realities together.
And what this all leads to is a massive philosophical shift, something called computation as ontology. That's a fancy way of saying that programming isn't just about solving problems anymore. It's about defining what is real within a simulated universe. The programmer, well, they become something like a demiurge, a creator of worlds, with the power to write their own laws of physics.
Which of course leaves us with a huge, provocative question to chew on. As we get better and better at engineering these complex, programmable realities, the goalposts start to move. The question isn't just what problems can we solve anymore. It becomes what new forms of intelligence, or maybe what new kinds of realities are we actually going to build?